Hello everyone. I'm Chuntao Ding. I'm glad to share with you our accepted CVPR 2023 paper. The main problem we solve in this paper is how to avoid task interference of using a single model to accomplish multiple tasks. In this paper, we propose the ETR-NLPs, which is composed of two complementary components, NLPs and ETR. NLPs to extract task-agnostic features and allow each task to choose optimal combinations of those features adaptively. ETR, a parameter allocation strategy that partitions the parameters into shared and task-specific branches. As shown, this is the overview of the proposed ETR-NLP. We first use NLP to extract task-agnostic features, and as shown in this figure, then we propose to explicit task routing to select appropriate features for each task. Our first motivation is can non-learnable primitives avoid task interference? As shown, different NLPs can extract different features. Given input image, we can obtain different levels of feature representations by NLPs, as shown in this figure. We hypothesize that extracting features from non-learnable primitives that are neither biased nor adaptive to tasks at hand can mitigate task interference in multitask learning. As shown in this figure, this is our proposed NLP model. It first uses various types of non-learnable primitives, for example, polling shift perturbation, and so on, with different hyperparameters, for example, cone size, sparsity, perturbation strength, and so on, to extract a dictionary of diverse features. Then those features are rearranged into groups by taking one output feature from each primitive. Subsequently, a linear combination is learned to compress features in a group into a single output feature. Finally, those compressed features from different groups are concatenated together. As shown, we observe that hard parameter sharing models with fully learnable parameters, the green curve, learn rapidly and then suffer from its degradation due to the conflicting gradients from task interference. Networks with non-learnable primitives, for example, the blue curve, do not suffer from task interference by design. Compared to a hard-sharing multitask network with a standard learnable convolutional layer, the green curve, MTN with NLP, the blue curve has better learning characteristics, learn more steadily, and not suffer from its degradation. Our second motivation is can explicit task routing avoid task interference? As shown, this is our proposed ETR explicit task routing. Our explicit task routing separates parameters into a common branch shared by all tasks and a task-specific branch reserved exclusively for each task. Providing more precise control over parameter partitioning among tasks. Note that only one task is activated during a forward pass for both the existing and our proposed parameter partitioning methods. As shown, we observe that networks with non-learnable primitives, the blue curve, do not suffer from task interference by design, while explicit task routing, the green curve, and ETR with NLPs, the red curve, do not eliminate but suffer less from task interference. MTN with ETR, the green curve, and MTN with ETR-NLP, red curve, does not eliminate task interference but reduce it to an extent. We do many experiments. We first show the effectiveness of non-learnable primitives. As shown in this table, we observe that first, all standalone instantiations of NLPs lead to promise degradation. The lack of diversity in the features is detrimental to predictive performance. Second, unlike standalone NLPs, our proposed NLP-based networks achieve higher precision and recall while requiring fewer learnable parameters and flops. Since NLPs extract task-agnostic and diverse features, they can prevent the network parameters from being dominated by one or more tasks and mitigate the mutual interference between tasks. Compared to the baseline architecture with standard learned convolution, NLPs-based networks significantly improve performance. We second show the effectiveness of explicit task routing as shown in this table. we observe that first, all parameter partitioning methods improve performance over hard sharing. Second, our explicit task routing strategy is more effective for alleviating task interference and improving performance on both image level classification and pixel level dense prediction tasks. As shown, ETR-NLP is a combination of ETR and NLP. We observe that our ETR-NLP is consistently better than the baseline methods while having fewer learnable parameters. Second, we observe that the performance gains become more prominent as the number of tasks increase due to the inherent minimization of interference between tasks in ETR-NLP. Finally, we also observe that parameters, partitioning methods, for example, task routing, max rooming, and ETR-NLP scale better than loss gradient balancing methods to a higher number of tasks. Again, we observe that ETR-NLP significantly outperforms the baselines in many datasets. Here we give our conclusion. First, this paper presents the explicit task routing with the non-learnable primitives model for multitask learning. Second, the ETR-NLP model introduces non-learnable primitives for extracting task-agnostic and diverse features and explicit task routing to extract task-specific features for each task. Both non-learnable primitives and explicit task routing can provide the flexibility needed to minimize task interference. And finally, experiments on multiple image level classification tasks and on multiple pixel level prediction tasks show that our ETR-NLP method significantly outperforms state-of-the-art baselines with fewer learnable parameters and similar flops across all datasets. Thank you, that's all.